Welcome back, class. Today's lesson is going to be a slightly different format than the ones I've done before. It's going to be more like a standard lecture. I've written up all the notes, and so I'm just going to present to you a little lesson about spring dynamics and simple harmonic motion. So I will reveal the notes, and we will just go through it. You may want to pause it to take notes in various places, and I'll try to let you know what's important, to circle things or whatever. Let's see. So I'm going to talk a little bit about springs. There's something called a spring constant, K. And let's see what I got here. There's a rule. It's actually an engineering concept called Hooke's law. It says that when an elastic material bends a short distance x, there is a restoring force F sub x equals to negative kx. In other words, you have a force that's trying to resist the bending. That's where the negative comes from, because it's going in the opposite direction that you're displacing. So this works for a spring too. If you stretch a spring, the spring is going to have a force pulling against you, and if you compress a spring, there'll also be a force pushing back at you, always in the opposite direction from the direction of the displacement, hence the negative sign. So this is called a restoring force. And this K is called the spring constant when we talk about springs. I think in Hooke's law in general, I believe it was called a modulus of elasticity, but we don't have to worry about that now. We're going to use springs, and we're going to use K to represent the spring constant, which is basically the ratio between the force and the displacement. So the larger K is, the stronger the spring is, right? The stiffer the spring is. It has a larger force for a given displacement x. So when a spring obeys Hooke's law, we call it an ideal spring. Of course, you know, no spring is perfectly ideal. Usually, if you just displace it a little bit, it's close to ideal. If you stretch it too far, you'll go beyond the ideal range, and it won't obey Hooke's law quite as well. Now, simple harmonic motion has to do with when you have a mass on the end of a spring. So one end of the spring is fixed, and you attach a mass to the other end. And we're assuming that there's no mass in the spring, just mass on the end. You deflect the spring, so let's say you stretch it or compress it, and then you release the mass. And you'll see it bounce back and forth in an oscillation known as simple harmonic motion. So if you have a mass on a spring, you'll see it'll spring up and down, or if it's on a table, it'll go side to side in a sort of a regular oscillation. And when something in this situation, when we have a restoring force that's proportional and in opposite direction from the displacement, we get this kind of oscillation, and it's called simple harmonic motion. It actually shows up in many places besides just springs. Things like guitar strings vibrating, or your vocal cords vibrating, or air waves are simple harmonic motions. There are compression waves. There's pendulums even. Many different situations that we'll learn about as time goes by. So there we go. That's introduction to simple harmonic motion and spring dynamics. Dynamics is the forces that go on with springs. So you have a force that's in the opposite direction from the displacement and proportional to the displacement. And you get an oscillation back and forth if you have a mass on the end of the spring. So let me go to our next page. I think I have to pull this thing up, otherwise you'll see that it's coming up. Okay, here we are on our next page of notes. So here's a spring with a mass on it. Okay, so when we pull the string out, a displacement x. Okay, here's this blue line represents equilibrium, or the spring at rest when it's not being, no force on it. So we're stretching it out this distance x, and at this point the velocity is 0, the position is x, and of course there's a force to the left because that's the restoring force pulling the spring back in. And also there's an acceleration. Anytime there's a force and a mass, there's an acceleration. So if we let go of this spring, So the only force is the force, let go of the mass, so only the spring is applying a force to the mass. The mass is going to accelerate to the left. At some point, it's going to get back to its original position. So now the string is no longer stretched or squished. It's right where it's normally at. So our x is 0, which means our restoring force is 0, and our acceleration is 0. However, because acceleration is, you remember, F equals ma, so if F is 0, a has to be 0. But v is actually at its maximum at this point. That spring has been accelerating all this time. It has not slowed down. It's decelerated but not slowed. Its acceleration has gone down, but its velocity has continued to increase to a maximum at this point. So that means that the mass of the spring, the inertia, is going to make that spring go past that neutral place and continue to compress itself. So then we end up getting all the way compressed. Okay, we reach this point here, and the velocity has gone down to 0 because the x at this point is negative. Okay, there's our x. It's to the left. So that means that the force is to the right, and the acceleration is to the right. So the spring has been slowing down. It's come to a stop at this point. V equals 0. So then it's going to head on back, get back to this place here, similar to where it was there at x equals 0. So the spring is now relaxed. It's not stretched or compressed. There's no force, so there's no acceleration. But there's some momentum, right? This mass has been moving. It's going to keep on moving. You've got a velocity, a maximum velocity here. But as the string stretches out, you've got a restoring force pulling the spring backwards against the stretch. So now you've got the force and the acceleration going this way. So you're slowing it down until it stops. And here we are right back where we started. Notice that that's the same as this situation at the top here. So this is why we get an oscillation of the spring. It's going to compress and all the way down, and then stretch all the way out, and then compress all the way down. So it's going to be a spring's going to, with a mass on, it's just going to be going back and forth in oscillations. So let's go on to our next page. See where this goes from here. Well, that back and forth oscillation is something that's called a sinusoidal wave. In other words, here we have x, that's the spring stretched, so it stretches all the way up to the right, then down to the left, then up to the right, then down to the left. Here's time going from left to right. So as time goes from left to right, the displacement maximum goes down to 0, then it goes down to negative maximum, then up to the positive maximum, through 0 again to the negative maximum. And in sine waves, we call the maximum stretch the amplitude. That's the height, the farthest distance from the neutral state is the amplitude. The period, t, is the amount of time it takes to do one full cycle to get back where it started. So this is kind of like uniform circular motion like we were doing before. It's all related. So that's the period, the amount of time it takes to get back where it started. And so we can set this up as an equation. You may remember that the cosine of 0, let me just make sure I got this right. I think that's kind of not right, actually. This should start over there. Okay, so I'm going to fix this right here because I'm seeing that the 0 line is really over here. Okay, so to make this really correct, here's 0. T equals 0 right there. Because we know that the cosine of 0 is 1. So it's going to be a maximum at time equals 0, but based on this equation right here. Okay, so that's t equals 0 right there. So really this axis should have been moved over. That's still the period, okay? But we could also measure from any same point to any other same point, and that would be the period. As long as it gets back where it started, that's the period. But this is time equals 0 right here, because the cosine of 0 is 1, and then the cosine gets less than 1, goes to 0, becomes negative, goes to negative 1. And so we have x equals a, the amplitude, multiplied, cosine maximum is 1, so we have to multiply it by a to scale it. And then we have something interesting here. We have omega t. Hold on just a second. I just got to get the phone. Okay, where were we? Sorry about that. So omega, that's an interesting piece there. Omega is our angular speed, and its unit is radians per second. By the way, time is in seconds, amplitude is in meters, and displacement is in meters. But this omega is a new piece, right? Radians per second. And we'll learn more about that as time goes by. But that basically, that's what tells you how fast it's going back and forth. Okay, it's sort of like frequency. It's inversely related to the period. The bigger the period is, the smaller omega is. The bigger omega is, the smaller the period is. Because omega basically tells you remember, radians is a measure of like angle, like degrees. So we're saying basically how many degrees does it go in 1 second. And remember that this is considered one cycle. So we'll go back to our circle analogy. That would be 360 degrees or 2 pi radians. Okay, so that's what we have here, 360 degrees or 2 pi radians. So we want to know how many radians does it do in a second. That's what omega is. So if we take how many radians per second, multiply it by the number of seconds, we get the number of radians. Then we can take the cosine of that to find out how high or low we are. So remember, if you're doing these kind of problems, now you don't want your calculator in degree mode. You want it in radian mode. Let's see what we got here. Yeah, and there's an error. Look at that. Okay, let's see if we can fix that right now. Oh, this way. I was wondering if that was going to be there like that. There we go. 1 cycle equals 360 degrees equals 2 pi radians. The period, t, is the time in seconds to make 1 cycle, or 2 pi radians. So now we're going to do a little algebra. Okay, omega is radians per second, right? So in t seconds, we know it goes 2 pi radians because that's the period, the amount of time it takes to go all the way around. So omega must be 2 pi divided by t, and its unit is radians per second. Of course, we know that frequency is 1 over the period. So omega could be written as 2 pi over t, but can also be written as 2 pi f. I think I better start circling some things that are let's see now. I think I got it right now. Let's see. What I want to do is, for instance, circle this here. Omega equals 2 pi over t equals 2 pi f. And this is probably a good one too. X equals a cosine omega t. Let's go back. What else do we have that's really important? Let me go back one more. This one, right? That's your basic spring constant equation right there. F equals negative kx. You definitely want that one. You definitely want, I think you don't, this one's just sort of explaining the dynamics, but you don't really need to write that down. This one is a biggie. X equals a cosine omega t. And then we have here that omega equals 2 pi over t, or 2 pi f. So now we'll go on to our next section here. Let's see, what have we got? Okay, we're going to do a bunch of algebra and even some calculus here. Now I know you haven't all taken calculus, but there are some derivations in here that without calculus you can do them with trigonometry and they become a real mess. So I would say the calculus people will enjoy seeing this, and the non-calculus people, if you want another derivation, it's in the book, but otherwise you can just live with the results for now and know that there is a way to do it. So let's see, there's x. X of t, x is a function of t, that's all that parentheses t means, it's not times t. X as a function of t is equal to the amplitude times the cosine of omega t, the angular speed, sometimes called the angular frequency, multiplied by the time. So, well, we know from calculus that velocity is just the derivative of position with respect to time. So we can take the derivative of this, and that's just going to be negative a omega sine omega t, because you calculus people may remember that the derivative of the cosine is the negative sine, and since you have an omega in here, you've got to bring it out. By the way, here's an important little piece here. Maximum velocity is the amplitude times omega, because if you look at this here, this piece here is just a sine. The biggest it gets is 1. So a omega is going to be multiplied by 1 at the most. That's the most velocity you'll have. Okay, so now if we take the derivative of the velocity, we can get the acceleration. So we're going to bring out another omega, and the derivative of the sine is the cosine. So now we have negative a omega squared cosine omega t. And this implies that the maximum acceleration is a omega squared, because you see here a omega squared is what's multiplied by the cosine. And the cosine at most is always equal to 1. Well, let's see what else we have here. Well, now we're going to do some interesting stuff. Remember Newton's second law, F equals ma, and of course we have Hooke's law, F equals negative kx. So, if we put those together, we say that F is negative kx is ma. Well, negative k, there's x right there. Remember, x is just a cosine omega t. Is ma, well, there's a right there, negative a omega squared cosine omega t. So if we divide both sides by negative a cosine omega t, you can see all kinds of things cancel out, and we end up quite simply with k is left on this side of the equation, and m omega squared is left on this side of the equation. So a little bit of algebra, we see that omega is the square root of k over m. Okay, there's another good one, little nugget there. So that means that, as I wrote here, the stiffer the spring, in other words, the bigger k, and the smaller the mass, the faster the spring will oscillate back and forth, because how fast it's oscillating is omega. That's the angular speed that it's going. If you think about it as going around a circle, it's going around and around at a speed that is determined by k. If k is large, it goes fast. Of course, if m is large, it goes slow. So if you put a bigger mass on the spring, it's going to slow it down. If you have a stiffer spring, it's going to speed it up. You kind of see this, they show it in the book. I wonder if I can describe it somehow. Let me make a fresh page. And I'm just trying this off the bat here. I'm going to grab a spring, actually. Alright, maybe I'll grab this spring right here, and I will copy it, and then I'll go back to my new fresh page, paste the spring. Alright, so now what I'm going to do is I'm going to draw a circle. Okay, let's see, our shapes. Yes, circle with a little dot in the middle. Imagine the spring is attached to the edge of that circle. What would happen as the circle goes around and around? Okay, as the circle goes around, what's going to happen? Well, okay, I'm going to make a line here to represent sort of some wall that this end of the spring is attached to. Now, let's see what would happen. Well, say this circle's going around clockwise, right? Then we'll assume the spring can sort of slide up and down. So if the circle has gone around some, the spring is going to have to stretch out a little bit. And then let's say it goes around farther to here. Okay, so now our spring's got to stretch out even more. Gets out to here somewhere. Now our spring's got to stretch out all the way to here. And so you can imagine as it goes around and around that circle, the spring is getting longer and shorter and longer and shorter as it goes around the circle. I wish I could grab the end of the spring. Maybe I'll use a line to represent the spring instead. That might be better. I think that might make more sense. So let's say that we've got, say, this arrow. Okay, and it's going from here to some spot. Or actually, instead of an arrow, let's go with something like this. Alright, that looks pretty cool. So, there it is. Now, imagine that this end of the spring is going around this circle. See what it's doing? It's getting longer and shorter, and longer and shorter, and longer and shorter. So while it's doing that, if we were to graph its length, we get a nice sine wave. Short, long, okay? And if we think about it in terms of degrees or radians, we got 0, 90, 180, all the way back down to 0 again, right? Or, let's see, what is this? Pi by 2, pi, 3 pi by 2, 2 pi into 0 again. So you can see this whole analogy between going around in circles and a sine wave. Because what would really happen if you were to graph this length over time, you would see a sine wave just like this. It would get longer and go back to 0 and then go, in this case, negative, but it's getting longer and shorter and longer and shorter and longer and shorter. So this is kind of the relationship between going around in a circle, circular motion, which we studied before, and now simple harmonic motion. They're really very similar ideas. So we're going to discuss this a lot more, and you're going to solve problems and get a lot more insight into it. But I hope this was a decent introduction for you. And I'll see you in class, and we'll go over it again. See you then.